The title of this note is Rate of Change in Tangent Lines. And the outcome is that you're going to be able to describe how does the difference quotient calculate instantaneous rate of change. So there's a couple of key vocabulary words there. We have some old vocabulary. So we know that slope is rate of change. So anytime you're asked to find the slope of something, you are calculating the rate of change. Likewise, if I say, what's the rate of change here, I want you to find slope. If I want the average rate of change, that means I want the slope, the rate of change between 2 points, or the slope between 2 points. When you have a line that touches 2 points in your graph, it's called a secant line. So here's the graph. If I want to know the average rate of change between this point and this point, let me call those A and B. I would connect them with a secant line, and I'd find the slope of that line, and that would tell me the average rate of change. So the average rate of change between 2 points, let's call them A and B, is going to be the slope. We know that slope, let me write all the formulas we know for slope. We know that slope is the rise over the run. The rise is how quickly you're changing in the y direction. That delta means change. It's the Greek letter delta, so we say delta y over delta x. The run is the change in the x direction. Another way we can describe the change is we can say y2 minus y1 over x2 minus x1. That shows how the y values and x values are changing. If I'm talking between A and B, that's my x1 and my y1. The first x is A, so it actually goes last. So B minus A. The y2 would be the output at B, and the y1 would be the output at A. So that's a formula if you want to find the average rate of change. But it really is just slope. So what we were just looking at for average rate of change was secant lines. But in calculus, we're more concerned about tangent lines. The information I'm going to share with you, I don't want you to write just yet. So if I want to find a line that's tangent, what I would do, let's say I have this curve here. Here's the so I can find the rate of change between A and B. But what if I want to know what's happening at exactly moment A? That would be a line that only touched that graph at point A. It would look like a tangent line. I want the slope of that line. The only problem is, for slope, I need 2 points, and I only have 1. So what I'm going to do is I'm going to go ahead and use the secant line, the one in green. And then what I'm going to do is I'm going to bring the endpoints closer and closer together. So instead of using that B, I might pick a point that's really, really close to A and draw that secant line. And I hope you can see that secant line, its slope is almost the slope of A. And I would try to get closer and closer and closer until eventually I reached the tangent line. So if I'm getting closer and closer and closer to something, in calculus we call that a limit. In calculus, you might be asked for the slope of a curve. That's kind of weird. We know that lines have slope. Well, now in calculus, curves can have slope. And when you're asked for the slope of a curve, that means we want the slope of the tangent line. So the next part, we are going to write. So I do want you to write in your notes, please write in your notes, that the slope of a curve means that we want the tangent to the curve. And if I want to find the slope of a curve at point A, what I'm going to do is I'm going to use that slope formula. You might recall that that slope formula we just saw looks like this. Here I have 2 points A and B. But I want them really, really close together. So I would just want them just a little bit apart. So there's A. And I want something that's really, really close to A. Imagine this is really zoomed in. I'm going to call this A plus H, where H represents just a little bit. So instead of using B, I'm going to use A plus H. And this should look familiar. And we see the denominator. So there's x2 minus x1, y2 minus y1. And the denominator, a plus h minus a, cancels out. And ideally, we'd love it if there was no space between those 2 points, because if there was no space between those 2 points, I would have the tangent line. I want h to be 0. I can't actually get there, but I can get really close if I say the limit as h approaches 0. This is how you find the slope of a curve at some point A. This needs to be memorized. Let me move that out of the way so you can see it. You must memorize this. And in fact, it's so important that this piece right here, the actual formula, has a name. It's called the difference quotient. Difference because of right there, and quotient because of the division part. So that is the difference quotient. So if you take the limit as h approaches 0 of the difference quotient, you will get the slope. So we're going to actually do an example of this on the next page. So let's find the slope of the curve y equals x squared when x is 2. Slope of a curve means I'm finding the limit as h approaches 0 of my difference quotient. It's going to be, this should be f of a plus h minus f of a all over h. And a in this case is 2. A is the number that you want to be at. So now I'm going to substitute a with 2. Okay. I'm going to keep substituting. I want f of 2 plus h. So that means that I am going to substitute 2 plus h into this function. So instead of x squared, it's 2 plus h squared. That's the input. Minus, again, instead of x squared, it's 2 squared. That's not a 4, that's an h. Now I'm going to do algebra. 2 plus h squared, you do need to FOIL that out. It's 4 plus 4h plus h squared minus 2 squared, that's 4. And I'm going to simplify. In the numerator, 4 minus 4 cancels out. Notice that in your numerator you have a GCF of h. I can factor it out if I want. And I have a factor of h in both the numerator and denominator that cancels out. So I have the limit as h approaches 0 of 4 plus h. So now you're going to calculate this limit using direct substitution. Substitute 0 in for h, and you get 4. What this means is that when you take the graph of y equals x squared, that's just your parent function parabola. When x is 2, if you draw the tangent line has a slope of 4. That's what the limit of the difference quotient was solving. It's the slope of the tangent line. We can also call it the slope of the curve. The slope of the curve is the same thing as the slope of the tangent line. You might also be asked to find a normal line. A normal line is perpendicular to a tangent line. It's the exact same process, except that the slope is the opposite reciprocal. So an example, let's use the same one. Y equals x squared. Let's do a different point just to have some variety. Let's do this at x equals 3. So I'm going to follow the same process, but I'm going to find the limit as h approaches 0 at 3. I'm going to plug 3 into the equation. So I have 9 plus 6h plus h squared minus 9, and the 9's cancel out. I really should be copying my limit notation, but I'm trying to save some time here. So the limit as h approaches 0 of this, and I can already see that the h will factor out and leave me with 6 plus h. And when I directly substitute 0 in, I get 6. 6 is the slope of the tangent line. So the slope of the normal line is the opposite reciprocal. You can think of 6 as the fraction 6 over 1. So the reciprocal will be 1/6. And because the tangent is positive, the normal will be negative. So the slope of the normal line is negative 1/6. So I used the same process to get the slope of the tangent line, and then I found the opposite reciprocal. Last thing we need to know is speed. Speed is an application of this. Speed is the absolute value of velocity, and speed is the instantaneous rate of change. So earlier in the notes we talked about the average rate of change. Average is the slope of a secant line. Instantaneous is the slope of the tangent line. So you would solve it just like you've seen those other problems. If you're asked to find the speed, then you need to find the slope of the tangent line. This is where the notes are going to stop, and we're going to practice this in class.